Tagadan 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 pam pam tagadan 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 pam pam tagadan 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 pam pam tagadan.
Good day, everyone. Thank you for joining us for day 2 of the 2-day HPC AI Advisory Council Swiss Conference and HPC XXL User Group. My name is Brian Sparks, and I'm the Director of Worldwide Operations for the Council, and I'll be today's moderator. We have a robust agenda for the next 4 hours with great topics and speakers from CSUS, Ghent University, Oak Ridge National Lab, Jülich Supercomputing Center, DDN, and Control IQ. I encourage everyone to ask questions via the chat QA window, and our presenters will try to answer them after their presentation. The QA window is right at the bottom of the panel. This webinar is being recorded, and the sessions and the slides will be available on Council's conference website over the coming days. With that, let me introduce you to CSUS's very own Hussein Araki to kick off the day. Hussein.
Pleasure to have the CTO of CSUS to give us this talk. It's the keynote for today, talking about this conversion of cloud. And Sadaf, stage is yours, and welcome for the next day.
Thanks, Hussein. Thanks, Brian. Thanks for the invitation, and thanks for attending. So I will first do the. I'm really happy to talk about this topic, which we are sort of at CSUS discovering gradually, but I will kind of start with a disclaimer. This isn't a security talk. It's like an HPC person talking about security models. So if it bothers you a lot, some of the wrong terminology, I apologize in advance. But I hope you see the connection related to this topic. So for this community, CSUS probably doesn't need a lot of introduction. Just I say a few things. We provide high performance computing, storage and analysis services to Swiss scientists and researchers. We do operate operational weather and climate forecasting platform service, which is in fact one of the H2 supercomputing use case. But we are not going to cover it today in examples. Then we offer large-scale data and storage platform and services for mission-critical projects. And this is the case partly I will cover today, as we had a project with the Paul Scherrer Institute with one of the use cases. And because we are a national supercomputing facility provider, and the data center also provides housing services to other IT operating facilities such as the Blue Brain project. So I will start with a perspective of our developers. So no matter which IT technologies we are targeting, HPC, edge, cloud, we would like to think about productivity of developers who exploit these environments, and then they need certain abstractions. So ideally, they can build on any other environment, be it a laptop or their own virtualized environment, but that build pipeline should be autonomous. Build and test pipeline should be autonomous. They do not need to be exactly on the target environment there. While which represents an operating environment, we operate under certain constraints. So for instance, as a supercomputing center, our constraint is to deliver high performance and scalable solution at any cost. And in doing so, we make sure that those deployments are secure from the perspective of users and developers, all the developers targeting that environment. And in a very high level way, we look at it from a perspective of a pipeline applications being built and tested autonomously, and data and compute and storage being shipped to an operating environment. So in a very abstract way, again, a developer is writing code, building it, packaging, and here for packaging, I use containers, but it could be any other packaging model. And I use it because we will talk about containers a bit. Then it is uploaded to some artifact registry or pushed there, and then pulled from there and run in an operating environment. And that could be any observational facility and instrument in cases of scientific instruments. Cloud, we all know, off-premise resources, and supercomputing, where large-scale simulations are typically run, and these platform operators operate those environments under those constraints. So if all goes wrong, we are all good. But as we will see that, and I have included a source here, and I will include in references here, that open source projects are spread. Specifically, open source community scientific projects and other projects are spread across many systems. And those systems are vulnerable to attacks at the system level as well as at the individual level. And here, a few of those vulnerabilities and attacks are highlighted. What that leads it to what is called like software supply chain attack. And if one part of the chain is compromised, the whole supply chain is compromised for the development, integration, and deployment of a software solution. And this is what we are going to really look into detail from the point of view of edge, cloud, and supercomputing ecosystem. So what I'm going to talk about are three things that we are largely leveraging in order to have convergence across these environments. So the first thing is API for HPC. So HPC accesses are typically not provided through secure APIs. There is a project going on. In fact, it started before the security concept were introduced for HPC at CSUS for programmability aspects of the supply chain of the software infrastructure ecosystem. The second thing, which is very important, is we will talk about is container engine for HPC. As I mentioned earlier, container here is like a packaging and deployment mechanism that provides this handshake or abstraction between the developer environment and an operating environment. And there we talk about a container engine that we have been developing called CSUS. And the third part, which I will not go into too much detail, is how do we in fact operate the infrastructure, which is called infrastructure as code for HPC. So all these unique aspects, they do exist in the cloud and in some cases edge environment, but they do not have robust, scalable, and high performance implementations in the supercomputing ecosystem. So very briefly, I introduce the REST API part. So there is like a little picture that highlights what does it provide. So just imagine an environment where a user targets an HPC ecosystem. Each individual supercomputing environment for submitting jobs, for doing data transfers are unique. So what users end up doing is they develop these customized, more often than not, vertically integrated environment for each HPC ecosystem. In the case of Firecrest, we targeted 4 aspects: accessibility. So it should be uniformly accessible from any device a developer is using, adaptable, support a diverse ecosystem, security, in this case, how the authorization control works in layers. We will talk about it differently, and it is programmable. So every time a new HPC system is deployed, they do not need to reprogram the system. And how it is being done is through convergence of cloud identity and access management using standard protocols such as OpenID Connect, using the policy agent and engines for fine-grained role-based access controls. And it sort of provides, as if you could imagine, a single entry point for other cloud service type of provider. It allows us to provide a single point for all resources. The container engine idea we are developing is not to provide the whole ecosystem, but leverage the part that touches the HPC, high performance and scalable aspects of running a container on a supercomputing system. And in this picture, what you see on the bottom part is that users can use any container packaging ecosystem, be Docker, to build those images. While what we provide is we provide the plugins, the integration with the HPC resource management system. So these containers almost transparently run on the target ecosystem. So the target deploy the rich tool chains, getting richer and richer every day, including the security aspect of container signing and metadata. And the Cloud Native Foundation DevSec of efforts, I would recommend having a look at it. Same, like users have autonomous build and testing environment, integration with CI/CD toolchain, integration with HPC infrastructure, and more specifically, native close to metal performance for accelerators like GPUs and job submission system. And users do not have to really, in most cases, think about if there is a different accelerator or a different MPI or a different proprietary network working underneath it. Very briefly, I plug in our next generation, in fact, it's already running, app supercomputer as infrastructure as code. So what does this mean? It means that we are using the cloud virtualization technologies, but offering bare metal and scaling. So the way you can visualize it is the following, that historically, if you know, or if you're familiar with like this guy, the clusters, specifically the HPC clusters, are named after speaks. And so ALF was kind of conceptualized as the underlying management and orchestration ecosystem on which the individual named HPC clusters with different QoS will work. I am not covering it today, and not also with the use cases, but it could be the analogy you can almost use as a virtual machine, as a virtual cluster, but with bare metal performance and scaling, leveraging multi-tenancy concepts, and offering some of the quality of service for different workloads, large scale simulations, or more sort of AI and machine learning workflows for container orchestration using Kubernetes. So I'll take a little pause and maybe ask if people kind of remember if this photo, not from very long ago. So it is this evergreen got stuck in the Suez Canal. And all you see are these containers up there. So in real world, supply chains can get disrupted for all sorts of reasons, and same could happen in the virtual world. Like in real world, supply chains can get, threatened or affected or have breaches. And the same can also happen in whether we are using container as a packaging technology or not. So how does this actually happen in the sort of world for software, if you look at it from a supply chain point of view? And the reason I'm introducing the supply chain concept is because if we look at the IT from an IT system or infrastructure point of view, edge, cloud, and supercomputing, the workflows will be running essentially these large scale supply chains to orchestrate these workflows. So if you recall, a couple of years ago, this SolarWinds attack came out, and essentially the system was not attacked directly, but it was in fact attacked through a software company which sells IT management products to the government agencies and private sector clients. And the whole extent, including the DOE, which do operate some of our peer sites, and there was no evidence that the HPC centers were affected or resources were affected, came out during that time frame. Almost like half a year ago, there was this presidential document came out talking about different aspects. I mean, this is a very good read. At first, I was suspicious, but then when I started reading it, it covers really some interesting aspects. First, they say we need to have like some trust and transparency in our digital infrastructure. And if I look at it from that point of view, today, or in fact right now, we are using a digital platform to communicate. I'm presenting you, and there are a lot of systems involved in making sure all works. And we have a big problem if things do go wrong. Then the other part it highlights is that, and as again using the example of Zoom in this case, that there could be systems providing a service or a software service that could be spread over cloud, on-premise, and hybrid. Again, the similar concept going behind edge cloud and supercomputing. Then this is the part I really kind of enjoy, reading and linking. It says it's like almost counterintuitive. It says that if we want to build these system with trust and transparency, the software as a service, platform as a service, or infrastructure as a service, we in fact have to stop trusting everything. This is essentially the zero trust model. And the final part was, again, enhancing software supply chain security, because we need to trust the supply chain in an independent, transparent way to ensure that things do work. So what is this zero trust security model? So very simply, never trust, always verify. In fact, if you have trusted something before or someone before, including users, applications, and resources. And this is like a little picture from an NSA document showing how, without zero trust, a validated and verified device and user through a validated device and user, someone can access the entire infrastructure resources without making sure that every time a user and device access, it is treated as a potentially a malicious access. So there are almost quite a few different ways of defining the zero trust security architecture. But I pick up the one document that was put by NIST, where they highlight 7 of them, meaning that data and compute services are considered resources, communication is secure regardless of network. The most important one, which we don't do in HPC, is the resources is granted on a per session basis. This is the strongest part of Firecrest. We have the policies are dynamic, everything is monitored, enforced, and a periodic feedback loop. So what happens in our world today? So some of you may recall a couple of years ago, including CSUS, quite a few HPC sites in Europe have been hacked through, SSH key account access. Because essentially people being set up, we have these single sign-on configuration once you access the environment. And it's not too difficult to argue in a case of zero trust architecture, it won't happen. What is the impact when something like that happens? You have to block access to the resources, scrub the system, clean everything, give new credentials, and start all over again. A lot of loss of productivity for scientists here. So needless to say, we don't do anything today. So the important thing is, how do we go from where we are to the next step? And it is a gradual process. In fact, I think in this document from NSA, it was put really very nicely. It's like a mindset where how do you treat access to system and resources. But we are technical people, so we cannot implement a mindset. So we have to translate into proper technical steps that we need to evolve at the data center, like CSUS. So here I'm highlighting 7 those steps. I use rainbow colors just to see, okay, all of them together make white. So cloud native standardized access gateways, fine-grained role-based access control, authorization, filter, and attributes for resources, extensive monitoring, logging, and enforcement, isolation and multi-tenancy and virtualization, so attacks can be localized, using microservices architecture for constant upgrades, and patches, because HPC centers are not supposed to do that. And again, automation, self-serving, and healing. We are not waiting for a human in the loop to come in and take actions. So here, very briefly, I will introduce a project we did a few years ago called Celvedas, which one could imagine as an edge to supercomputing project, where edge is an experimental scientific facility or instrument. And Celvedas stands for Services for Large Volume Experimental Data Analysis, utilizing supercomputing and cloud technologies. So on what you see is Paul Scherrer Institute for Light Source, which is their 3rd generation of synchrotron light source. And CSUS is a specific experiment beamline, which they use as part of this co-design project. So as an edge system, their constraint is to provide low latency access to computation and data analysis to scientists using that equipment. Then, because the data that is being generated is huge, and then it requires extensive communication, which is not on-site or on-premise, they ship it to our environment, namely high-performance scalable computing and data analysis on BizDyn and the tape laboratory. The reason they have to look for this, they are expecting a massive growth of data, from a few petabytes and in a few years going to about 100 petabytes. One option could be they could build an infrastructure on site or a data center, but this model, one could imagine, it won't scale. So the edge operators, while operating on their constraint, they have to, in an independent way, work with HPC operators so that they can extend transparently their IT infrastructure to other devices. That was our target. So again, a very simplified workflow for the solution that was developed as part of that project, and there is the architecture of that part. So on the PSI side, they have their workflow that involves collecting data from experiments, doing compute, and their users, it's not CSUS users, their users, they then transparently access the resources at CSUS. And while the orchestrator or operator on their side access CSUS resources such as reservation service or data mover service to run jobs on CSUS resources transparent to their users. As a solution, the APIs are used so they can target any other system. If, for instance, if BizDyn is not there, it could be other similar cluster, and the interface is abstracted through the API. And as part of this work, they accelerated the application using GPUs, again, built on their local devices and run transparently on a supercomputing ecosystem. So their edge operators here are, in that case, making sure the environment for their end users doesn't change, while we on the HPC side ensures that the constraints on our environment have been met. So how it was done. So here you see like a high level architecture of Firecrest. There is a internet facing gateways. based on a microservice for authentication, authorization, and traffic control. It's cloud compliant OIDC token management that allows this per session management, the utility services that essentially provides a layer that is missing, the identity and access management layer that is missing on top of HPC resource access. So out of 7, what are the technical steps that are covered by the design of Firecrest? Again, a cloud native single access point or access gateways to services. We are not there yet, but that's our target. Fine-grained access controls. You can add additional filters and attributes to control access based on resources, such as for reservation service. So someone can only have access to one type of service, extensive monitoring and logging. And because the architecture is microservices based, can be updated very quickly and rapidly without the whole entire system getting through an upgrade. So here, you can see the workflow of PSI, where the data has been generated from one beamline and then stored on the tape drive, while then the users can come in and upload data from the tape and process on HPC system. So what they needed, their operator needed, were access so that to some privileged services, because they do not have admin access to our environment and ecosystem, and but the type of access they wanted required some privileges. And so they can, from their user point of view, they can operate it as it's their own resource. So Slum reservation service, again, if you know Slum, you know it is a privileged operation, but it is an interface is created so that privileged operation is allowed through an API to a selected set of users. And now you can see they can program it in a way so that based on an experiment, timing, and needs, they can create a reservation on the system through which people can submit jobs. Same is done for the data mover, so they can take that data, refurnish it with the metadata that is needed to operate on an HPC system. And then again, we provided an interface so they can transparently, again, with proper access controls and parameters and attributes, perform that operation. And from a point of view of two operating environments, there is an edge operator, an HPC operator working together with proper separation of concerns, making H2 supercomputing work in an environment. In the interest of time, I will be very quick with containers for HPC. I think in this advisory council, there have been talks from my colleagues on Saurus. So in essentially, build anywhere, run on HPC, if it is run on HPC. So the aspects of zero trust model that are important here to highlight are cloud compliant isolation and virtualization, but as well as the HPC specific features, which I mentioned already. So out of 7, the 2 that are targeted here are the ones listed here, isolation, multi-tenancy. And so these containers are natively designed for that, and the microservice architecture and CI/CD pipeline. Here are some results from the containers that were built and run on BizDyne, and it shows the performance and scaling on the GPUs. So just recapping a bit, going back to developers, environments, extraction, and operating environment constraints, what is happening in the container world for security, there are a lot of activities going on that we can leverage easily, but one thing to highlight, there is no silver bullet. So Open Source Security Foundation is doing a lot of work. There is this SALSA call project. And again, the good thing about this is that it's not all or nothing. There is support for gradual agile adoption. And there are many projects that can help if someone wants to start going in this direction for as an individual open source project or as an infrastructure provider. And we are expecting some of your HPC resource provider providing some of these standardized tools and services. So just reflecting on the chain I showed earlier, with this, we could really identify and isolate and fix problem and stop access infecting the whole supply chain in this process using these tools. Again, changing mindset using these three things we are doing at CSCS: API for HPC, container engine for HPC, and infrastructure as code. We are addressing different aspects of these rainbow, which help us achieving close to much more close to a cloud native security model, so we can interoperate. But I would like to highlight, this is very much indeed work in progress. Some of these technologies we have been working at CSUS were introduced for different use cases, and now we are adapting and extending them to target some of these edge to cloud workflows. But this is gradual, and this is really very, very hard. At the conclusion and future outlook for us as a resource provider, the developers maximize the usage of an environment, and they make their experience is a measure of success. That they build these scalable high performance applications and use these resources as part of their workflows. So the abstraction for them for building packaging need to be converged in a cloud edge and supercomputing platform. Otherwise, we lose productivity. And these should be easy, accessible, and common, because we are talking about a large number of developers targeting these diverse ecosystems. Platform operators like us need to be dynamically reestablish trust with human and machine users accessing our ecosystems. And we can only do that if the resources the workflows are targeting, such as the one I mentioned earlier, have a similar model for establishing access control and trust. The reason being that the overhead in establishing these things in a variety of different ways is not only in terms of learning experience for users, but also removing this abstraction mean we need to really work with a large number of tools, which would make the interoperability almost impossible. So we need to establish a model, and then we can have some common and interoperable tool chain for automating these access and controls, and not go for a custom solution between PSI, for instance, in this case, CSCS. Standardization and in some cases legislation can help, but also if we standardize and legislate before a problem is understood, it may also create some issues. So again, highlighting the three topics I covered during the talk. I will upload the slides so you can access the references for CSUS and Firecrest, for ALPS, which is, and users are already running on a virtual cluster on ALPS called IGER, and the two documents which I extensively referenced during my talk. So with that, and again with the picture of Lugano, I wish we had an in-person meeting. For those of you who don't know this one, this is like the pumping, cooling water from Lake Lugano contraption coming to CSCS there from Lake Gianni. Okay, so I can stop now and happy to take questions for the next 10 minutes. Sorry, I rushed a bit the container part, but I thought this community have heard already SORUS quite a bit. So should I stop sharing or leave the screen on?
No, leave the screen on, because the first question that I have is, I think from a few slides back, this audience member raised the question. So which application is using or is being used as the data mover service?
Okay, so CSCS, I'm going to give like a bit of a detailed answer here, because there is a data mover service at CSUS that exists and based on Globus that allows users to stage in data in and out of the system for running jobs. So in that case, that data mover service is available to all users running HPC simulations on PIS9 for quite some time. In the specific case of PSI and Celvedas, I don't know what is the application in this context, but they in their context they had sort of an in-house pipeline for moving data where the original workflow to augment the data stored in CSUS tape library had to be transferred back to PSI for processing. And by doing through this data movers, if I can qualify this data mover solution as a data mover from archive tape library to online, the applications using in this case are specific to PSI because they are the only one who know how to translate the metadata that is needed for running simulation on an HPC ecosystem. So I hope kind of I answered. So, so the CSUS has, overloaded usage of data mover terminology.
Thank you, Sadaf. Hussein, do you have any questions for Sadaf?
Well, I think it will be biased if I ask Sadaf question, but it's but I would yes, I would still ask a question. This is back to containers actually, and this is one of the questions has been raised earlier by others, talking about what's the best approach for maintaining performance on not paying performance in containers, and how do you see that that will be possible, and what's a strategy of CSUS to do it? So I'll be like in the part of as if I am outside CSUS asking this question.
So I can maybe be a bit cheeky here. I mean, do we really know all the time we are getting the best performance out of really powerful HPC systems all the time? Yeah. So provided, okay, we start with the assumption we have the best performance or a baseline performance, and the container will through the virtualization layers, you can lose it. And the short answer is yes, you can. Because it's from a point of view of an application that is, let's say, built on PIS9. If it is natively built, it is really using all the bells and whistles of, let's say, Cray proprietary MPI with its all the environment variable settings, etc. One thing, it's using let's say Cray Maths library to link with the scalable BLAS. Or if an application is built very close to the native hardware and software stack, then you say I build it on my laptop using the virtualized environment. By the time you end up tuning it to a target environment, you will be much better off probably building it on a target ecosystem. So from the perspective of building, packaging, shipping, in this case, for me, the developers should have the choice. They say that because I want the native target performance system and I do not want the portability and autonomy I would like to maintain on my laptop, for instance, or a package I don't download from NVIDIA GPU cloud, that's a developer's choice. So to me, we should really be very careful in contextualizing the usage of container. Container is a separation of concern solution for our community. And if a use case doesn't need it or doesn't want it, we shouldn't use it. It's like any other tool. If a tool is misused, it won't work for you. Having said that, if an application is tuned for a given MPI library and for a given GPU and a parallel system environment, the Saurus team and many other activities have shown that the performance loss is very, because you get through this pass-through native MPI or close to native MPI performance and GPU performance. We need to really be very careful about the whole application
context.
packaging tuning life cycle.
No, I think I completely agree with you, because I think we have seen this situation when we're comparing applications by running in a traditional CPU and GPU. Some of the applications were ready, and then we moved them there because it would just gain from it. Otherwise, if it won't gain, it just continue to be in the CPU. Or if it was not ready because it doesn't have the entire context from all application library and what's needed. Maybe you can, if we compare that to GPU, that could be also being a close, let's say, comparison between what we have seen early with the time of the GPU and now today with the container.
Yeah. Yep. So there is a question: what is the benefit of using container if you have to use a vendor-specific library? So maybe I can read it in one way or the other, and then whoever asked the question can comment. Does it mean if you have to use the vendor-specific library, or if for building your app, you don't have to?
Yep.
Like MPI is a very good example, or you can even almost call it the MPI with some bells and whistles like GPU. So if you don't have to use a vendor-specific MPI library, you can use containers. But if you have to use, like I said, for using, in the case of BizDyn, some of their specific optimization for certain message sizes or message patterns, of course, then you don't want to use a container. It's like in the physical world that I ship everything inside my big container, or I do a personal one-to-one, personalized transfer, because I'm concerned that my package would break or it will not be treated.
Yesterday we had during the talk of DK, actually we touched this part, and and he mentioned that he'll be very happy to contribute there and try, because he did not start working at this level, but definitely he is looking at it. Because he's now working and collaborating with Azure and other cloud providers, which could be sharing other stuff.
Yeah. So the person clarified, your question was related to earlier comments on Cray MPI. So Cray MPI is a normal MPI, but people who would like to get the maximum performance or tuning out of the system, they end up using some customer like environment variables and other things. So, and I used Cray MPI as an example to answer Hussein's question, because he said, how can I avoid losing all the performance I had as a baseline on my native build if I build or package my application on an environment that is not BizDyn? So that was
somehow related, but yeah,
that was the
clear.
reason. Yeah,
That's clear. Anyway, the machine is customized enough to give us all this freedom, and where we can running in the best way possible. Thank you very much.
Okay, thanks.
Tigadan tigadan pam pam tigadan 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 pam pam tigadan 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 pam pam tigadan